In the field of science, the huge mysteries pertaining to what existed prior to the gigantic explosion have sparked mixed conversations and fascinated scholars for quite some time. This enormous question tests more than just our ability to decipher the universe. It challenges the actual boundaries of human knowledge. Imagine yourself at the brink of existence, examining the colossus shadowing and pondering what lay there before our universe was conceived. The event of the Big Bang marked the beginning of all things, including time and space. But was there a moment earlier? Could there have been a state of nothingness, a state of calm before the cosmic gathering began? If so, was it truly nothing? Or was there something far more profound that existed before the beginning of time? As we delve deeper into this question, science takes us on a journey past insight into the beginning of the universe, testing our conscious awareness. Physicist Brian Cox, known for his investigations into the wonders of the universe, suggests that something surprising might have existed before the massive explosion. He urges us to reconsider our perception of the world and existence. In this investigation, we dissect the science, the speculation, and the dazzling insights that could make sense of what existed before all that we know. We will explore ideas like cosmic inflation, quantum fluctuations, dark energy, and even multiverses. The answers we uncover might paralyze you, but they might also open new understandings of our place in the universe. Get ready to dive deep into a realm that defies imagination and science, where the obscure still captivates scientists, leaving them floored and sometimes even unsettled. To appreciate what may have existed before the Big Bang, we first need to carefully analyze what the Big Bang was. According to scientists, the Big Bang defines the point in time when the universe became extremely hot and dense, rapidly expanding to set off the development of all matter, energy, and fundamental forces. When we look toward the night sky, we see proof of this hot beginning with galaxies spreading out from the initial point. But why did this happen, and was there a period before this dense, hot start? According to the theory of cosmic inflation, there was indeed a before, and it was far from void or peaceful. Cosmic inflation suggests that before the Big Bang, the universe was in a cold, vacant, and loose state, resembling a vast vacuum. However, this vacuum wasn't entirely empty. It contained an immense amount of energy that fueled the rapid expansion of space itself. This expansion, called inflation, happened so quickly that it laid the groundwork for all that followed. In a fraction of a second, space expanded at unimaginable rates before slowing down, with the energy transforming into particles of matter and the forces we observe as the Big Bang. But what was the nature of this energy? Why did it suddenly grow? The universe? And why did it stop? Experts believe that this cosmic inflation created patches of the universe, each experiencing its own Big Bang. Imagine a fabric stretching endlessly, with tiny bubbles forming here and there, each bubble representing a universe, including our own. This idea, called the inflationary multiverse, suggests there could be limitless Big Bangs and an infinite number of universes. Our own is just one of many. This enormously complex reality challenges our understanding of the universe itself and leaves us with the question, what else is there? The notion that there was nothing before the Big Bang is speculative, not definitive. According to our current understanding, even if you removed all energy, particles, and radiation from the universe, it would still not be truly empty. Dark matter, dark energy, quantum fields, and other forces weave an intricate tapestry of something, even in its most vacant form. Even if we tried to remove everything, the interplay of these forces would leave the universe generating new forms of energy. This reality alone bewilders scientists, as it suggests that true nothingness might be impossible within our cosmic understanding. Space itself has constants, rules, and properties that prevent it from being completely empty. Imagine creating a region with literally nothing in it, no particles, no radiation, except for quantum fields and fundamental constants. These would still exist, implying that this non-existence has properties. For example, there is a phenomenon called zero-point energy, which represents the lowest possible energy state of quantum fields. In this state, particles can temporarily appear and vanish, creating an unsettling resonance of movement, even in what should be empty space. This challenges our idea of a true void and suggests that yes, even before the Big Bang, there was something that scientists are only beginning to understand. One of the most astounding theories in modern cosmology is the possibility of eternal inflation. If inflation caused our universe to exist, it may continue forever. Brian Cox describes an astonishingly vast inflationary multiverse, where universes are infinitely produced and continuously expanding. Imagine each Big Bang as a flash, lighting another universe, while inflation continues in other areas, forming countless other universes. This cycle could, in theory, go on for eternity. This idea of vast universes gives birth to an enchanting concept of a fractal universe, where each new universe might create its own Big Bang. Every universe is its own independent domain, unaffected by the others due to the rapid expansion of space. This hypothesis excites and unsettles researchers as it suggests a never-ending multiverse with no definitive beginning or end. Imagine our universe as just one piece in a giant cosmic structure, forever expanding and constantly creating new universes. What if the disturbing reality is that there is no before or after, but rather a timeless universal pattern developing and deteriorating? Our ability to interpret nothingness changes when we consider quantum field theory. According to this theory, the universe is not just a collection of matter floating in space. Rather, it's a complex network of energy fields that fill the universe, interacting to create all that we observe. These fields are like invisible seas, with waves or particles acting within them. Even if fields are at their lowest energy level, known as the vacuum state, particles can appear and disappear momentarily, borrowing energy before returning it. This phenomenon results in virtual particles, entities that briefly exist and then vanish, leaving only a faint memory of their presence. The concept of virtual particles casts doubt on the notion of a true void. Imagine an empty universe where all matter, radiation, and energy are removed. Would it be nothing at all? According to quantum field theory, it wouldn't. Even in a vacuum, fields would remain active, occasionally creating transient particles. This constant movement in what should be nothing suggests that the universe doesn't acknowledge our notion of emptiness. The fields and forces endure, filling the universe with a hidden energy that prevents total inertia. This understanding raises an intriguing question. If fields produce particles and particles make matter, could the universe itself have emerged from this void filled with quantum fields? Dark energy is a mysterious force that currently drives the accelerated expansion of our universe. But did dark energy exist before the Big Bang? Some perspectives suggest that the dark energy we observe today is a remnant of an energy field that existed prior to our universe's formation. Dark energy's properties hint at a colossal hidden force that might have existed before the Big Bang. Certain hypotheses propose that dark energy, in a much stronger state, could have driven the inflationary stage, causing rapid expansion. The presence of dark energy suggests that even if our universe were stripped of all matter and radiation, this force would continue to expand the fabric of space-time. This thought leads to an unsettling question. If dark energy was present before the Big Bang, could it have shaped the circumstances that led to the birth of our universe? It's possible that dark energy is the silent architect of inflation, or even the moment when our universe began. As we explore this possibility, we face the potential of dark energy as more than just a force shaping our universe, but as a key that could unlock the secrets of the multiverse itself. Another theory that offers an alternative to the Big Bang as the ultimate beginning is the theory of cosmology suggests that the universe goes through endless cycles of birth, death, and resurrection. In this model, the Big Bang is not a single event, but rather part of a timeless rhythm where universes expand, collapse, and then regenerate in another cycle. This theory suggests that the universe we live in may have been reborn from the remnants of a past universe. The process of contraction and a cyclical pattern of expansion would entail that there was never a true beginning, but rather an endless series of universes that are growing and changing over and over again. Cyclic cosmology raises significant questions concerning the notion that time itself might be cyclical rather than linear. If this theory is correct, it could indicate that the preceding Big Bang was merely an additional version of the universe, one that collapsed only to give birth to our current universe. Researchers say that this theory has the potential to answer questions about ultimate origins, proposing that there is no true beginning since in some form the universe has always existed, challenging our ideas of time and existence. Early stage. Gravitational waves. Another intriguing concept is early-stage gravitational waves, which may entice clues about what existed prior to the Big Bang. Gravitational waves are ripples in space-time caused by massive cosmic events, and scientific theories suggest that these waves, if ever detected, could reveal new understandings of the universe's earliest times. These waves might serve as reminiscences of the past Big Bang. If identified, they could provide evidence of the universe's previous iterations. The possibility of discovering early-stage gravitational waves is one of the most exciting prospects in cosmology today, as it might not only reveal the truth about the Big Bang, but also offer a glimpse into the cosmic state before our universe was born. This theory presents an enticing possibility of detecting gravitational waves that could act as fingerprints of a pre-Big Bang universe, pushing the boundaries of understanding as we continue to explore what could have existed before the Big Bang. We delve into concepts that push the boundaries of our understanding, challenging even our most fundamental presumptions regarding space, time, and existence itself. One of the most mind-boggling ideas comes from the study of quantum gravity, which aims to meld general relativity and quantum mechanics. This merger could potentially reveal a unified theory of everything and might offer insight into what existed prior to the Big Bang. Quantum gravity suggests that space and time are not continuous, smooth entities as we experience them, but instead are discrete, granular structures. According to this theory, the fabric of space-time itself could have originated from a microscopic Planck-scale structure, with tiny quantum fluctuations shaping the universe in ways we cannot yet fully comprehend. In this view, what we perceive as the smooth continuum of space and time might have emerged from these fluctuating quantum fields. Thus, the before of the Big Bang could be described by a radically different concept of reality, one where space and time themselves were not fully formed. The string landscape and the multiverse. Another possibility is that the universe is part of a vast cosmic landscape filled with potential universes, each with distinct physical characteristics. This theory, based on the string landscape, arises from string theory, which holds that all fundamental particles are actually tiny, vibrating strings. In this framework, there are many possible configurations, each representing a different set of physical laws. The string landscape might suggest that our universe is only one of many, emerging from its own distinct Big Bang-like event. Such a landscape also suggests the idea that other universes might have different strengths, dimensions of gravity, or even different types of matter. In this view, our universe might not be unique, but rather part of a multiverse, a collection of universes, each evolving independently. The multiverse theory provides a speculative yet fascinating answer to the question of what came before the Big Bang, another universe in a different configuration, possibly leading to endless cycles of development and devastation without a definitive origin. Black holes and the birth of universes, in addition to these cosmological models, some theoretical. Physicists have considered the role of black holes in shaping the nature of the universe. A hypothesis gaining attention is that our universe could be the result of a black hole formed in another universe. In this scenario, the singularity at the focal point of a black hole could serve as a gateway to another universe, with the Big Bang being the moment when such a black hole created our cosmos. This theory is supported by the fact that, according to the theory of general relativity, the singularity at the center of a black hole is a point where space and time curve infinitely, creating a region where the known laws of physics may fail. The extreme conditions inside black holes may result in the development of new universes, suggesting that our Big Bang was just the birth of our universe from the singularity of an ancient black hole. The nature of time. Exploring these concepts requires a deep dive into the very nature of time itself. Some cosmologists speculate that time, as we understand it, may have had no meaning before the Big Bang. If time began with the Big Bang, then there may have been no before in any conventional sense. According to this view, time itself might have emerged from a quantum fluctuation or from an initial state in which the common distinctions between past, present, and future did not apply. This could lead us to reconsider the idea of causality, which relies on the assumption that events happen in a linear sequence. If time did not exist in the way we experience it, then the question of what came before the Big Bang becomes nonsensical, as there would be no temporal framework to support it. Cyclic time and primordial. Soup, complicating the picture, are theories of cyclic time. As mentioned previously, cyclic cosmology suggests that the universe undergoes endless cycles of birth, evolution, and eventual collapse. In this model, the Big Bang could symbolize merely the most recent swing in an eternal series of universe cycles. These cycles might not be identical, but could evolve in different directions, each with unique physical properties. According to this theory, the universe would be a continual process with no true beginning or end, rendering the question of what came before the Big Bang meaningless in the conventional sense. The idea that time itself might be cyclical implies that each Big Bang could be followed by a contraction and another big crunch, with the universe reinitiating itself in an endless loop. Another avenue of investigation into the nature of the cosmos is the potential of a primordial soup of bits and fields that existed prior to the formation of galaxies and stars. This idea suggests that before the universe began its rapid expansion, it was filled with a dense and hot mixture of elementary particles comprising quarks, leptons, and bosons in a state of extreme energy. These particles would have been interacting at extremely high densities and temperatures, laying the groundwork for the formation of matter and energy as the universe cooled. Some versions of this theory suggest that this primordial soup existed in a quantum foam, where particles constantly emerged and vanished due to the uncertainty principle of quantum mechanics. The soup's properties have the potential to offer insights into the universe's beginnings and, by extension, what preceded the Big Bang itself.